This is Dr. C, and we're going to be looking at threads and processes and the difference between the two as a lead-in to how to actually manipulate them in a program. Let's begin by asking the question, what is a process? A process is a program in execution. It is run under the control of the operating system. It has all the details associated with it that the operating system needs in order to do what we call a process switch from one process to the other. And as part of the deal with the OS protects processes from each other, from stepping on their memory or instructions. So what you see here is something you might find in a typical Windows display when you go to the Task Manager. This is a list of all the processes running on my computer under Vista. You can see there are quite a few processes. Besides the applications you currently run on the desktop, there are a lot of stuff going on in the background that actually operates as a separate process. And the job of the Windows operating system is to keep these processes away from each other, but to also give them access to the CPU in a timely time. So here we see what might be the origin of the idea of a process, when back in the early days of computing we had to schedule time on the computer, and so not a very efficient way to take advantage of an important resource. So here we see the definition, official definition of a process. It is the operating system abstraction that describes what's needed to run a program. Technically, it's a sequential stream of execution of a program in its own address space with its own data, its own variables. And you also often see the term task used synonymously with the word process. So what does a process have to know? A process is essentially a data structure that maintains the ID of every process. When it's created, it must have operating system support to allocate memory to the program so it can keep track of its data, its state. During the execution of multiple processes, the CPU is assigned to one of those processes that actually gets the CPU. So in a way, it's a contention, supports contention of the processes for CPU. And again, it also needs to be removed, reclaimed, resources freed by the operating system. So on a single CPU system, remember, only one process can be running at a time. So what does a process have to know? Well, remember, a process is a program in execution, and so the process is in charge of running a program. It has to maintain the program's counter so it knows where to pick back up when a process is interrupted by another process. It has to maintain the CPU registers, because all those registers have to be replaced and put back into place when the process comes back in. Scheduling information, priority, for example, memory management, what access does the program have to various aspects of memory, account information, charging, for process use, CPU use, I/O information, whole wealth of information that goes on when you have a process. So here we see the state that processes can be in. Remember, the process is under the control of the operating system, and operating system will move the process into a variety of states. So it's admitted into the system. A new process arrives, it's now ready for execution, but so may be a number of other processes. So until the scheduler hands off the CPU to the process, it's not running. So it can be in a running state. When it's in a running state and does I/O, it typically becomes interrupted and waits, whereas so other processes can come in and take over the CPU. So the basic idea is to maximize CPU resources, and the CPU does, the operating system does this through maintaining various states that a process can be in. So we've seen a process. Now what is a thread? Well, within a process there's the ability to launch separate concurrent activities, and these are called threads. So threads exist within a single process. The difference is all the threads share the same data and address space of the process. So they're all kind of part of that same process family. And here we see an example of how a single process with multiple threads, now it has the threads in a way competing for the CPU within the process. Here in a multi-core computer, we see the same kind of scenario, except things are now a little more complicated because of the fact that we have multiple cores. But threads and processes can share those cores. Now, this makes things a lot trickier for developers since we're kind of in uncharted territory with this. So why do we need threads at all? Well, they provide parallel computation with low overhead, and we want to use them when a program, a process, needs to wait for some resource such as disk access or network connections and still wants to do work, so they can shift the work from one thread to another. So while one thread is waiting for something to happen, another can jump in and do some work. So to summarize, we have threads and processes. Processes live in their own address space. They operate independently from other processes on the system. The downside of a process switch, of course, is the overhead, since everything, all the registers and all the auxiliary information needs to be saved and then brought back in. Threads, on the other hand, are much more lightweight than a process. They share the address space of the program. Minimal overhead occurs when you do thread switching. They are extremely useful, but can be quite dangerous if not understood and can lead to some really nasty errors. So that's the scoop on processes and threads.